Log on, tune in, find out. Another good idea from Cambridge.
Thanks for inviting me here for this program, and thank you very much for coming to my talk. So I will talk about how to play unique games against semi-random adversary. It's joint work with Alexander Koller and Yuri Makarychev. And this talk is a little bit computer scientific. I'm not sure if it has connection with discrete analysis. So tomorrow Yuri will give a talk which has much more connections with analysis. So if you have any questions, please feel free to interrupt me and ask those questions. So in this talk, I will try to explain the title of the talk. So I will talk about the unique games conjecture. And in a certain way, unique games conjecture is a mini version of P versus NP question, and it deals with a certain problem which is called the unique games problem. I will define the problem and tell you some results. And then I'll describe the semi-random model and give algorithm for the problem. I won't tell you why this is a game, and I won't tell you why it's unique. Though maybe at certain point you can guess why it's unique. And I want to start with some kind of very brief, in a way, history or motivation for the problem. In general, this is one of the key problems now in approximation algorithms, and it's useful to have some kind of to have a problem, combinatorial optimization problem in mind. And one of such problem is a max cut. And in this problem, you have a graph G, and the goal of your algorithm is to partition this graph G into pieces so as to maximize the number of edges cut. This is just one of the problems. It's quite important. It played an important role in the history of approximation algorithm, but just in a way, just one of the examples. And so what's known about this problem? So the problem is NP-hard. So if you want to find exact optimal partitioning into pieces, you essentially can do it efficiently in polynomial time. So we may want to find an approximation algorithm. What's an approximation algorithm is? So this is an algorithm that finds an approximate solution, so another partitioning into pieces, and of course it cuts not the maximum number of possible edges, but rather some other number of edges, and the ratio between the worst ratio of the algorithm, so between the number of edges cut by the algorithm and the optimal value, is called the approximation ratio. And of course we want to be this approximation ratio to be as close as possible to 1. For example, if the approximation ratio is 0.99, it means that the algorithm always outputs a solution that's within 1% of the optimal solution. So in 1972, Karp showed that max cut is NP-hard problem, which essentially means that, again, we can find an algorithm, that exact algorithm for this problem, efficient algorithm. So on the positive side, for this problem, half approximation was known for a very long time. You can use the greedy algorithm for the problem, or you can just use a randomized algorithm. Just partition the graph into two random pieces. Then the probability that any edge is cut equals exactly to a half. So the solution output by the algorithm will cut just half of edges on average, which gives you right away half approximation, because the optimal solution in the worst case cuts all edges. In 1992, in seminal papers on PCP theorem, Aurora Safra and then Aurora Land, Matwani, Sudan, and Segedi show that actually not only you can't find the exactly optimum solution, but you can't get solution of cost 1 minus epsilon of optimum, where optimum is very small. So there result implied probably 0.999, something like that. But still, you can do very close to the optimum. And still, nothing better than half was known at the time. So Gomans and Williamson in '93 introduced semi-definite programming to techniques to combinatorial optimization. So these techniques, I will talk actually about them a little bit more later in the talk. They in a way an analog of linear programming, but are much more powerful for many combinatorial optimization problems. And after their work, similar techniques in definite programming was applied to many other different problems. So the approximation ratio they got using semi-definite programming is 0.878. And there was this gap between almost 1, slightly better than 1, and 0.78. Then Hastad combined techniques of PCP theory with some new techniques that use Fourier analysis on the Boolean cube, and got a better non-approximability result that you can do better than roughly 95% of optimum. Still, there was a gap between what you can do and which is sort of probably you cannot do. Till in 2004, Hodgkin-Kindler, Mosel, and O'Donnell closed the gap. So they showed that actually you can do better than the algorithm of Gomans and Williamson. So at that point, we knew that 0.878 is the best possible approximation, but there is a catch. So their result relied on the unique games conjecture. And so this conjecture says that certain problem is hard. And while there is some evidence that the problem is NP-hard, we don't know for sure whether this is the case or not. And after that work, similar results, hardness results, were shown for many other problems like max cap, vertex cover, graph coloring, max CSP, etc. And all of them relied on this hot conjecture. So essentially, without the conjecture, we also have some non-approximability results, but they're usually much weaker. And that's why we are interested in this conjecture. So what's unique games conjecture? The conjecture deals with a certain problem called unique games. So we have a graph G on n vertices, and we would like to color it with k colors. In this picture, we have 3 colors. But there are constraints that we need to satisfy. So for every edge UV, we have a permutation of colors. So we know that if one vertex is colored with one color, then the other vertex should be colored with other color. And so this correspondence is 1-to-1. So in this example, for example, we know if U is colored with yellow, then V must be colored with red. So again, for every edge of the graph, we have such permutation by UV. Permutations for different, of course, edges may be different. And so our goal is to color all vertices with these colors so as to maximize the number of satisfied constraints. And by looking just at the problem, you may think that it's easier. Because you can start with one vertex and then uniquely propagate colors from one vertex to the other. And actually, this uniqueness is the reason why the problem called unique games problem. The catch is that your goal is to find such solution, for instance, where not all constraints can be satisfied. So indeed, if this problem, this instance is satisfiable, then you can, in linear time, find the optimal solution that satisfies all the constraints. However, it's not clear what you can do if 1 minus epsilon fraction of all constraints are satisfiable, and this simple propagation algorithm fails in that case, and there is no obvious way in fixing it. So this was the reason why Subhashwat made the following conjecture: assume that your instance is 99% satisfiable. Can you find a solution that satisfies only 1% of all constraints? Or more formally, assume that for any epsilon and delta, there is sufficient large number k, the number of colors, so it's NP higher to distinguish between instances that are 1 minus epsilon satisfiable and delta satisfiable. Okay, so is the statement clear? Any questions so far? But again, you may think that just the instance is 99% satisfiable, and the goal of your polynomial time algorithm is to find some assignment with, of colors to vertices that satisfy 1% of all constraints. So what's known about the problem? So of course, the first thing you can do for such problem is to write some kind of relaxation. Linear programming relaxation would be the first step, and for simple linear programming relaxations, it's easy to see that they don't work. Then HDP relaxations and Hot and Vishnu in 2004 showed that actually semi-definite programming doesn't work for unique games. So essentially this means that semi-definite program, I will actually define semi-definite program a little bit later, says to you that the instance is satisfiable, then there is a good solution to the problem, but indeed there is no good solution. And these gap examples were then strengthened for stronger relaxation, not for semi-definite programming, but Shirley-Adams and Shirley-Adams plus HDP in the series of works. So we know that any sort of known relaxations cannot disprove unique games conjecture. There were a number of algorithms proposed for the problem. Most of them are based on semi-definite programming. So the first algorithm was proposed by Hot in the same paper where he stated the conjecture. Then there were some improvement by Trevisan and Gupta and Talwar, and we obtained an algorithm with joint work with Charvikar and Yuri Makarychev, which given an instance that is 1 minus epsilon satisfiable, finds a solution of value 1 minus square root epsilon log k. So here epsilon and delta, so we always assume that in the optimal solution 1 minus epsilon fraction of all constraints are satisfiable, and sort of our goal is to find the solution where delta fraction of all constraints are satisfiable. And this algorithm turns out is the optimal possible. So Hot, Kinder, Mosel, and O'Donnell showed the following: that if you can improve the performance guarantee of this algorithm, you can do better than actually you can disprove the unique games conjecture. So in a way, there is a threshold. So we know that you can do you can achieve this approximation guarantee of delta equals to 1 minus big O of square root epsilon log k. But if you do any further, then you can distinguish between any constant epsilon and delta. So their hardness result relied on the unique games conjecture itself. So in a way, it's still some kind of boosting result, a boosting of hardness. And because of these results, there is no way we can improve approximation algorithms for this problem without just disproving the conjecture. So then people started thinking about natural families of graphs for which the unique games conjecture can be true, and particularly one such instance of graph which has many applications in computer science is expanders, and Collett and Tulsiani and then Aurora et al. Essentially disproved the unique games conjecture for expanders. So we know that if the underlying graph G is an expander, then the conjecture is false for such graphs. So on expander, you can distinguish between delta and 1 minus epsilon divided by h, where h is the combinatorial expansion of the graph. So if the graph is expanding, then the conjecture sort of falls. Another natural families for which the conjecture could be true is based on this instance of Hot-Vishnoi. So Hot-Vishnoi showed sort of presented instances for which HDP doesn't work. So we could hope that those graphs are actually hard. But Alexandra Kola showed that actually for instances on this Hot-Vishnoi graphs, there exist algorithms that solve the problem. And another work, so many hardness of approximation results use something called parallel repetition, which is similar to taking tensor products of original instances. And Barak et al. Showed that actually by building instances in such a way, you can disprove the unique games conjecture. So if you start with an original, with some mildly hard instance, and then take sort of a tensor power of that instance, that you won't get in the end a hard instance, which is usually the case actually. So usually parallel repetition works for other problems. And there were some other directions. So recently there were some results for sub-exponential algorithms. There were some conjectures proposed that are harder than the unique games conjecture, that are weaker than unique games conjecture. People started thinking about quantum algorithms for unique games. So the summary of this introductory part is that we have this unique games conjecture. Yeah.
What do you mean by quantum algorithm?
Using quantum computing. But that's wasn't that much explored. There is one work on that, but it deals with a different problem. Anyway, this is pretty much off topic. I just mentioned it. It has nothing to do with the talk itself. What we know now is that the unique games conjecture is very important for approximation algorithms because many different algorithms depend on it. Essentially, this is a barrier to improving many algorithms. And we don't know whether it's true or false. And what's more disturbing, we don't really have any idea how hard instances look like. So this is very different from, let's say, P versus NP problem. So while we don't know whether P equals NP or not, maybe all problems are in fact easy and can be solved in polynomial time, we have at least some ideas how hard instances should look like. For example, if I give you a product of two random prime numbers that are of the same magnitude, then we believe that factoring the product is hard. Not NP-hard, but is hard. And many cryptographic systems depend on this fact. So if you, let's say, implement some algorithm that can factor any number, it's easy to verify whether the algorithm works or not. We can just empirically give to this algorithm many products PQ and test whether it can factor those numbers or not. And similar statements are true for NP versus P question. We know how hard, at least how hard instances of such satisfiability problem look like. We believe that some other approximation combinatorial optimization algorithms are hard. For example, if you have certain graph, random graph, and then you increase density at certain portions, it's believed that it's hard to find that area where graph is denser than, so we increase density. So we have a way of constructing hard instances. And this is not true for unique games. We have no idea whatsoever how hard instances should look like. We only know that if they're constructed in a certain natural way, then they're easy. Or in other words, we can solve those instances. And the question we ask whether random instances of unique games are easy or not. But just looking at completely random instances is not interesting because those instances are indeed easy, we know that. And maybe the reason why they're easy is not the correct one. And one of the reasons, of course, is that the underlying graph for any completely random instance of unique games is just an expander. So let's look at this question in more detail. And first, we describe the model. So any instance, any hard instance, let's say we believe in the unique games conjecture, can be obtained in a completely adversarial model as follows. So first, the adversary chooses the underlying graph G. So this is just an arbitrary graph. Then she chooses a set of constraints on this graph. And she chooses a set of the constraints in such a way that the instance is 100% satisfiable. At the next step, she picks epsilon fraction of the constraints in a special set denoted here, E prime. And the final step, she replaces these constraints in the set E prime with arbitrary new constraints. So just from the construction, it's easy to see that this instance is 1 minus epsilon satisfiable, right? Just because after the second step, we obtained an instance which is 100% satisfiable, then we chose a set of size epsilon, and we changed those constraints. So in the worst case, only edges in the set E prime are not satisfied by the original assignment of colors. So what happens if we change one of these steps, one of these 4 steps, and make it random? So suppose that, for example, the third step is random. So again, first we choose any graph, then, so this is adversary chooses the graph, then she chooses arbitrary constraints so that the instance is satisfiable, and then we choose randomly epsilon fraction of edges. And finally, she is allowed to change constraints on those edges as she wills. So we prove that in this case, the instance is easy. Means that we can find a solution to this problem in polynomial time. More specifically, if we have an extra constraint that the average degree of the graph is at least log k, where k is the number of colors, then with high probability, an instance coming from this semi-random distribution is easy. We can find a good assignment of colors for it. Okay. Any questions so far?
What is a linear game? Linear unique
Oh
game?
yeah, so linear games are special type of games where constraints not of arbitrary form but special form, and they correspond to certain family of linear equations. That's why this is interesting. Actually, yeah, there is another formulation which is kind of almost equivalent. It's called linear unique games. And we use semi-definite programming for it. And let me start with just introducing the standard semi-definite relaxation for the problem. So in this problem, we introduce for every vertex u of the graph and color I, we introduce a vector ui. So sort of in the intended solution to the program, or canonical solution, we let ui be some fixed unit vector, or just you can think of that vector as number 1 if u is colored with I, and 0 otherwise. So given any real solution, any real coloring of the graph, we can construct this intended solution or canonical solution. So again, ui is just indicator of the event that u is colored with color I. The number of unsatisfied constraints then equal to the sum. So we sum over all edges, and then we sum over all colors ui minus v pi uvi. So it's easy to see that if an edge is satisfied with the coloring, if the constraint is not violated, then this sum equals to 0. Because if ui equals to 1, it means that u is colored with color I, and therefore v is colored with color pi uv of I, and it means that v pi uv of I also equals to 1. Now, if the constraint is unsatisfied, then exactly two terms in that sum equal to 1. So one is ui, where I is the color of u, and another one is sort of vj, where g is the color of v. So this sum exactly equals to the number of unsatisfied constraints. So essentially, by solving this semi-definite problem, and our goal is to minimize this quantity. So here is the picture. We have this graph G, and for every vertex color pair, we have its own vector. Again, we have some vector configuration in mind, which we would really want to get this intended solution. But when we solve the optimization problem, we may get, of course, very different vectors instead. So this is the problem we get. We would like to minimize number of unsatisfied edges. So the objective function measures the number, not the number of satisfied edges, but rather the number of unsatisfied edges. So particularly, we know that if optimal solution the optimal solution has value 1 minus epsilon, then that quantity is less than epsilon. So in this form, actually, it's epsilon times the number of edges. So we can add extra normalization divided by the number of edges, and then that quantity will be less than epsilon. And then we add constraints that sum of squares of these vectors equals to 1. Again, in our intended solution, this constraint is clearly satisfied just because only one vector from one u1, etc., uk equals to 1, and all others are equal to 0, which means that every vertex is colored with exactly one color. We require then all vectors u1, etc., uk are orthogonal, and we add some triangle inequalities, which are not very important for this talk. So L2 squared triangle inequalities for these vectors. And the natural way of thinking of this semi-definite relaxation is that the semi-definite relaxation gives you describes a distribution over solutions of unique games. So the intention is that ui squared is sort of the probability that u is colored with I. And particularly this constraint says that every vertex is colored with a certain probability, with one color with probability 1. And then the inner product of two vectors, ui and vg, gives you sort of the probability that u is colored with I and v is colored with j. And this constraint that all vectors u1, etc., uk are orthogonal tells you that events that u is colored with I and u is colored with some other color j are disjoint. But this is, of course, only intention. So in fact, the solution of semi-definite problem doesn't give you such distribution, and that's kind of the main problem in obtaining a good sort of integral solution or intended solution from a solution of semi-definite program. So the reason why we introduce this semi-definite relaxation is because we can solve it in polynomial time. And most algorithms I told you about before use exactly that relaxation. The problem with our model that we can show that this semi-definite relaxation does not work. Essentially, if a graph has a hidden hot Vishnu instance, I'll explain it in a second, then the relaxation fails. So, as I said before, there exist examples of graphs with constraints where SDP value of the solution is let's say epsilon over 10, which means that HDP sort of thinks that instance is very satisfiable, almost satisfiable, but there is no integral solution. There is no real solution to the problem. And let's try to hide such a solution in our instance, semi-random instance. So suppose that this is a hot Vishnoi graph and this is a hot Vishnoi instance. So the adversary will choose at the first step this graph, and then on this set of colors, yellow and red, she will choose these constraints from hot Vishnoi instance. And then she will add two extra colors, let's say blue and green. And on those colors, she will define just identity permutations. So obviously, the combined instance is satisfiable. Just because we can choose, let's say, blue to be the color of every vertex, and then all constraints are satisfied. And once we add this hot Vishnoi constraints, the graph is still satisfied. Let's look what happens when we introduce this noise where we randomly choose edges. So edges are chosen randomly. Let's say we chose these edges. But the adversary now corrupts these edges in some very special way. She doesn't touch the hot Vishnoi instance, but she changes the constraints between these new two colors, blue and green. So she, let's say, introduce random noise between them. So she corrupts this pair of vertices and this pair of vertices. Now what we get is that the instance, since we chose epsilon fraction of edges, the instance on blue and green colors is now roughly 1 minus epsilon satisfiable, because we corrupted epsilon fraction of the constraints. The instance on yellow and red colors is not satisfiable because it is hot Vishnoi instance. However, HDP value on those edges. So if you restrict HDP to red and yellow, the HDP value will be epsilon over 10. So HDP thinks that this is a satisfiable instance. And what happens is that since HDP can find a good solution, HDP solution on this colors red and yellow, it will assign all the mass to that instance, right? Because the best it can do on green and blue is only epsilon, and for red and yellow it's epsilon over 10. So the HDP will assign 0 vectors to actually two good colors, blue and green. And we won't be able to recover any good solution from those vertices for which HDP assigned non-zero vectors. Of course, the specific instance is sort of simple because here we probably could separate instances into pieces, but in general, you can make it more complex, and any approach based on the standard HDP relaxation fails. And this is a problem. So what we do, we introduce a new sort of semi-definite program, but it's interesting that this semi-definite program is not a relaxation. So what we do, we require that so essentially in the previous, so we change only one constraint from the previous HDP. We require that all vectors now are unit vectors. So before, we required that the sum of u1 squared plus etc. uk squared was equal to 1. And this is the strange thing to do because the intended solution doesn't satisfy this constraint. And what essentially we say is that the probability of choosing every vertex is 1. Alternatively, of course, we could put 1 over k. So the most important part here is that all lengths are equal, which intuitively says that probability of coloring every vertex with every color should be the same, which is obviously false for many instances. And particularly, this is not a relaxation, and the objective value now doesn't have any meaning. So before, if HDP value was epsilon, we could hope to get a solution that satisfies 1 minus, let's say, epsilon constraints. We couldn't really get it, but we could get a solution that satisfies 1 minus epsilon times the approximation ratio number of constraints. And here the HDP value, this number doesn't have any meaning, and this is easy to see because even satisfiable instance may have very bad HDP value. So let's say similarly to what we had before, we have a graph, and if we color every vertex with blue, then the graph is satisfiable, but we have some strange permutation between other colors. So the HDP portion corresponding to blue vertices indeed contributes 0 to the solution, but the contribution because of vectors corresponding to other colors can be very large. So if we know that HDP value is 1 or 2 or 3, we don't know whether the instance is good or bad. So now let me describe the algorithm, and we need this notion of label extended graph. So look at this instance, and let's draw all edges corresponding to permutations. So if here permutation, in this permutation, green, if U is colored with green, then V should be also colored with green. We draw an edge between these two vertices. So the vertices of this graph are vertex color pairs. So this is our graph. This is a label extended graph. And so it's drawn again. And we say that an edge in this graph is super short if the distance between the vector ui and vj is less than square root of c log k, or ui minus vj squared is less than c over log k for some absolute constant c. So here is a picture. Suppose that for this vertex we assigned this vector, and for other this vector, then you see that vectors are almost collinear, so perhaps this distance is small. So this edge is super short, but if vectors look in different directions, then the distance is large and the edge is not super short. So once the algorithm solves this new HDP, it finds a set of super short edges and essentially removes all other edges. So we are concerned only with super short edges. And we prove a structural result saying that with high probability, any semi-random instance of unique games has many super short edges. More specifically, if you look at any original solution, 100% satisfiable solution to the instance, so to the instance that was obtained at the second step, right before we introduce some noise to it. And this solution is denoted by xu, so x sub u is the color assigned to u at that moment. Then there are many super short edges of the form uxu vxv. So in the previous case, for example, if before we introduced noise, a valid coloring was coloring with only color blue, then among edges connecting two blue vertices, there are many super short edges. So this is a statement of the theorem. Okay, is it clear? Any questions?
In what field do you apply this problem?
Unique games? No. So, well, let me answer it in the end of the talk, okay? And this is a good news. So, because in a way it's easy to deal with super short edges. So the reason for that is that if we use semi-definite programming algorithms like rounding algorithms, then such edges are easy to deal with. So a typical algorithm would take a random Gaussian vector and project all vectors on that vector, and then look at those vectors whose projection is sufficiently large, and pick those edges and as those vectors UI. And so if we have a color vector UI that whose projection is bigger than the threshold, we will color U with color I. So if the threshold is large enough, we can guarantee that with high probability there is only one vector UI, meaning that there is no another vector uj, because ui and uj are orthogonal, and thus the probability that both ui and uj's projection is above the threshold is rather small. And the threshold of C over log k guarantees you that if an edge between two vectors is super short, then it's very likely that if ui belongs to the set of chosen vectors, then vj also belongs to the set of chosen vectors. So this is the good news. The bad news is that for such algorithms, so this idea from our earlier work on unique games, we really need to know some probability that ui should be chosen. So these probabilities for different colors for u should be different, because if you do something similar to what I just explained, it's we can first color u with some color which is really bad for u, and that vertex won't have any super short edges at all, because it's not from the original solution. Even though our structural theorem tells us that there are many super short edges, those super short edges only correspond to our original solution. So once we start applying such algorithm, we will end up with some really bad solution, because it will pick all colors from sort of layers of these unique games that do not correspond to the real solution. And we need to fix it. So the algorithm finds super short edges and remove all other edges. And then it tries to recover sort of probabilities of choosing every color for every vertex. And it does it using linear programming. So for every vertex u and color I, it introduces this probability pui, and one of the constraints of the linear program is that sum of pui's over I over all different colors equal to 1, which is a natural condition to have. And then we maximize the number of short edges that we get if we choose UIs according to this probability. Specifically, we maximize sum of minimum of PUI PVJ, where UI VJ is a super short edge. And once we do this, we essentially use the algorithm similar to what I just explained, but if we choose UI, we project it, and the projection is above the threshold. But if we know that its probability PUI is really small, then we throw it away. Essentially, after any vertex ended up above the projection, we toss a coin again, and depending on PUI, we keep the vector UI in the set of chosen vectors or not. And those tosses of coins are not independent for different vectors, which is important. So we use techniques from our earlier work and find a good coloring. So now let me very briefly explain how the proof of the structural theorem works. Essentially, we show that if you have an HDP solution that has a few very short edges corresponding to some integral solution, to real coloring, and we have that real coloring, we can change this HDP solution in such a way that we get a better HDP value. So note that we don't know this HDP value. It still can be pretty bad, but we can just replace some vectors with new vectors and get a better solution. And the algorithm, also the proof uses just probabilistic argument. We fix one possible HDP solution and show, let's say that has few super short edges corresponding to the integral solution. We show that with high probability over choice of edges that we corrupt, this HDP solution is not optimal because it can be improved. Okay. And then we just use union bound over all possible HDP solutions. And in general, number of possible HDP solution is huge. So we use Johnson-Lindner-Strauss projection of that solution to low dimensional space, actually constant dimensional space like 5, for example, to reduce the number of HDP solutions, and some other tricks just to bound the number of different HDP solutions. Oh, yeah. And while semi-random instances, as we showed, are easier for small epsilon, so our proof works if epsilon less than 1/3, 1/3. Once epsilon becomes large enough, the problem becomes hard, surprisingly. So if epsilon equals to half, so if we could choose half of all edges randomly, then semi-random instances would be NP-hard, assuming actually 2-to-1 unique games conjecture. 2-to-1 unique games conjecture is another conjecture by Subashkot, which is similar to unique games, but is a little different. And there is no connection between these two conjectures known. So what's interesting about the proof is that we introduced a new semi-definite program which has never been studied before, and it's very surprising that it's not a relaxation, because combinatorial optimization usually all semi-definite programs or linear programs are relaxation, meaning that you have some intended solution. So you take this solution that correspond to a real solution to the problem, and it's a feasible solution to your program. And in this case, it's not the case. And to conclude, let me know that similar questions perhaps are interesting for other combinatorial optimization problems, because many problems are known to be, let's say, hard in general, but all practical problems, all problems you get in practice are not so hard. So even though it may be the case that the worst case approximation ratio you can achieve is pretty bad for a problem, in practice the approximation ratio can be much better. And for such problem, people try to study, to develop good models to say what a practical problem is. And one such model is just look at random instances. But that model is not so good. So maybe we can model similar problems with semi-random instances. And actually, our model, semi-random model, is not the first semi-random model. So there was some study of such problems before, but those models are a little, I think, a little simpler than this one. So maybe one can extend this work to some practical problems and show that in practice many algorithms perform much better than their theoretical guarantees. Okay, and that's it. I think. So any questions?
Now, there is an article by James Case in the CIAN of some months ago that the SPD is related with the algebra mass, which is important for railroad minimization of railroad in Holland.
Right. So semi-definite programs.
Because you say that there is no any connection.
Between what and what?
You said.
No. This is in general semi-definite programming was used like before. So before '94, I think semi-definite programming was used. I'm not sure whether it was used in practice a lot. After that,
Maybe theoretical.
right. After that, I mean, people thought about using semi-definite programming, but then Gomez and Williamson introduced semi-definite programming to get an algorithm for max cut, and many other semi-definite programming algorithms were developed afterwards. So this is a very powerful now technique in theoretical combinatorial optimization, and perhaps in practical as well. Even though there is a...
Do they have just algorithm, or they have existence theorem with the proof that they get the optimum?
No, no, it's known that we can solve semi-definite programming optimally in polynomial time, almost optimally, but that's essentially optimally. So there is a caveat that most semi-definite programming solvers are not very fast, but it's probably unrelated topic.
And if you say in the last part that you say if there are some programs, you ask the question, no? In the last,
right. So the question is,
if you have, for example, if you have to maximize two criteria, then what you do? You maximize first one and then the other one.
So no. So the question is the following. So, for example, for TSP, the best known algorithm now, there is no, I think there is no good hardness known. At least I don't remember. So for travel salesperson, the best known algorithm is 1.5. So you can get 1.5 approximation, okay, whatever, 1 over 2/3, right? But somehow in practice, people can't find solution which is 5% or 1% worse than optimal. So the question is why?
The algorithm, but the theory of it, if you have two functions, you have all these multi-criteria optimization,
Right.
which are not very good.
Depends on the problem, right?
Yeah, okay, you get Pareto, whatever it is.
Sure.
But much better is the lexicographic programming, first one and then the other one. But then the...
No, first of all, this has nothing to do, right, with multi-criteria optimization. And the other, in multi-criteria, you want to balance between two thresholds, right? So lexicographical won't give you...
But in programming, you don't do this.
Okay. Maybe you can continue the discussion
Right.
later, and if other
Do you
other
have the
questions?
reference and the paper of this?
Right, it's actually on my website, yeah. It's available from my website.
Okay. So if there are no other questions from the audience, let's thank the speaker again.
And what do you have this problem?
Sorry?
In what